the ideas we're covering today is diffraction, the outcome of the double slit experiment, which you can see is here, like that's basically what's going on, and the idea of diffraction grating as being more effective than Young's double slit experiment. So, if I just recap quickly before we get to diffraction, we have so far covered, right, if I put this down here, in a very dodgy way, what is that? What is going on there with that ray of light? Reflection. Okay? So we know, and you guys are expected to know, that if light hits a surface, it is going to reflect. And we have an angle of incidence equal to an angle of reflection. We've also covered the idea that you have a boundary surface, and if you have two different mediums, so say air and water, we have a normal. If I was to shine light to that boundary surface, what would happen to the ray of light? It would do what? Bend and refract. So far in terms of your language, you are expected to know reflection, refraction, and now diffraction. So if I was to walk right here to Amara's desk, I can't move past here. I would have to bend around to get around there. I'm diffracting. I'm bending because I hit a surface. Okay? So, you bend it like Beckham. So here, the idea is that wavefronts, so the lines here are like the crests of the wave. So it's like we're looking at the top of ocean waves. So the waves are moving this way, but they're now being stuck. And they have to move through a very defined opening. So what ends up happening is, here where it's free to move, it keeps on moving forward. But here, it has to bend to allow for the fact that it has to go around. So it actually diffracts around the entrances. And the smaller, okay, the slit, well, let's call it a slit straight away, the smaller the opening, okay, the more it's going to diffract into diffract faster. So far now we've got the language idea that we have diffraction, okay, and diffraction being the bending of light, and this angle of diffraction depends on how large the opening is. So coming back to some more language before we keep moving on, this idea of waves undergoing interference isn't new. So last week we talked about the idea that waves will interfere with each other and will have constructive and destructive interference. Now, coherent waves, when we talk about coherent waves, so coherent is another piece of vocabulary. Coherent waves means that they have the same form, the same wavelength, the same frequency. They're the same wave, okay, the exact same type of wave. They're just being produced at different points. Okay, so here they're produced at different points. So we knew that water waves would undergo interference, and in 1801, Thomas Young, he passed sunlight, which again means that the waves are coherent if it's all sunlight, through two slits, and actually found that he ended up with a situation where there was points on the screen, so he shined the light through two slits, and rather than, so if we look at it from the surface, he discovered that here, if he created two slits, so two openings, and shone the sunlight through, so this is the wavefront, shone it through onto a screen, so here we're looking at bird's eye view from the top, rather than seeing light the whole way, he didn't see that. He saw points of light. And that's that whole idea that how do you have, if I've got light shining, how can I all of a sudden have periods in which there is no light? And that bore the whole idea that, well, waves, water waves, destruct and cancel each other out. So light must be a wave. So we know about constructive interference. We know that when you have two coherent waves, so coherent meaning the same wavelength, the same frequency, when they're moving together, okay, they will constructively interfere when they're superpositioned, so put on top of each other, okay, they will enlarge, they will get larger. We already know from last week destructive interference happens when you take two coherent waves but you put them like 180 degrees out of phase. Okay, so where one had a maximum amplitude on one side of the axis, the other one has it on the other side. So they perfectly, okay, cancel each other out. So this one here, positive, this one here is negative, the exact same size, you end up with completely cancelled. And this is the whole idea behind Young's double slit, is that you end up with these points where the wavelengths, right, I've got a better diagram coming. So if you imagine this is looking at the wave from 2 dimensions. If I wanted to have the wave front sitting on top of this, it would be like the wavelength sitting like this. So here, you know, the waves are coming like this. So this is the crest. Oh, I didn't draw that very well. So there's the crest for that wave. And then here's the crest for this wave. So the crests are meeting together if we look at it from the top, but from the side, this is where it's conceptually hard to sort of show. If we looked at the waves from the side, more like this, as they're moving through, they end up finding these points in which they sit, and there's two positive amplitudes, and they end up constructing. So what does that give us? If we look at it differently, a different diagram. Now, if you want to, there's going to be a link if you want to look at the geometrical proof of it. It's coming. And we'll just keep on looking from a few different ways of thinking about it. So here, if I have light, now light we accept is a wave, and the light's coming through. Okay, again, the wave fronts are coming like this, and because they're going out in 2 dimensions like this. Okay? But there's infinite times in which they are then bending. It's because they're bending in 3 dimensions. So it's like it's a 3-dimensional movement these waves have. So there'll be points in which, from this 2 sources, so source 1, source 2, they will constructively interfere and therefore make a point of light. And you sort of notice the distance there is there. So if we put that on here, and then there'll be some points half a wavelength in distance less, in which they are perfectly destructing, so cancelling each other out. So Young's double slit actually gave us these ideas where if we look at it, you have, from the wave fronts coming, these points in which the 2 wave fronts have constructively interfered and formed a maximum where the light is, and then points in which when you put the wave fronts on, they have destructed each other. So one's, and it's hard to see, there's a wave crest here, but underneath there's no light at all, and that's the trough. So a crest, if I have 2 waves, if I have a crest, and then the other wave is at a trough, they're going to destructively interfere. And that's what's happening. The reason this gets so tricky is because you have to think kind of 3-dimensionally. These points here cancel out and destructively interfere. And when they destructively interfere, there's no light. Because light is just a wave. And it's like looking at water waves, and you end up with this pattern, okay, of light and dark, and light and dark, right? Now, of course, and I asked the other class this to think about it, of course, on either side of these here, right, outside of here, you're going to have points in which the waves are not going to 100% cancel each other out. There's going to be a point just on this side here. So here, the crest on crest, so it's maximum wavelength. It's like a maximum addition. But you're going to have, like it makes sense that you're going to have points on either side of the maximum. So the maximum is like having, you know, this same wavelength, you know, put on there, so you end up with a much larger wavelength. But on some of the other sides, right, you might have this wavelength, and then you might have, right, oh no, you don't have that. Oh, sorry. You might have, let me do it better here. You might have it slightly out of phase. So it's should be lower. So you have the same wavelength, same frequency, but they're out of phase. So this one plus this one adds here, then they go there, but then this is here. So you end up with it being slightly less light. I know my drawings, I'm just trying to rush. So you're going to end up having points in which they're not 100% constructively interfering, not 100% destructively interfering, but they're less light volume. And that comes back to last, we kind of did that last week in superposition, where you added the two waves together, and they don't always cancel, and they don't always double. There's in the middle points. And that's what's happening around these fringes. Okay? So I use the word fringe. Comes to the next slide. So the idea is that when we have here's my blue wave fronts. The black is sort of the boundary. I've got my two slits here. This will produce a maximum light intensity in the middle, because the waves have to travel the least amount of distance. Okay? And this is called the central maximum, and it's a type of fringe. Okay, so it's a fringe. We also then having from this central maximum, the next point, which we actually call m equals 1, it means it's one fringe away from the central maximum. So the central maximum we call m equals 0. The next bright fringe would occur when m equals 1, and it's slightly less light because the waves have had to travel further. So the waves, this is the least amount of distance they have to travel, but the waves have to travel further to get to this light point here. Okay? So these ones are our bright fringes. And there'll be the points here where we have the dark fringes, because the crests and troughs are exactly on top of each other and they cancel 100%. There's no light. So if you want to go into like the math, there's a whole heap of mathematical proof and a whole lot more. It's about half an hour's worth of videos if you want to watch them. Okay? But we're only going to really look at the mathematics of it. Okay? In terms of from formula perspective. So we have, in terms of applying Young's double slit experiment, we are going to use, for bright fringes where the light is, this formula, d sine theta equals m lambda. Now, the d represents the distance between the slits. So if you're given a question that asks you to use Young's double slit to find something, that d is between the two slits. We have an x, which is the distance between the slits and the screen that I'm looking at the light. Okay? And then we have, always the central maximum is smack bang in the middle. And then we have a distance between the central line and then the next bright fringe. And then we have a distance again between that and then the next bright fringe. And as the fringes go out, they get less and less light intensive because it's getting further and further away. The waves have to travel further, and as they travel further, they lose energy. Makes sense. We can find out the angle between them by looking at the ratio between the distance between these and the screen value. And this all comes into the idea, this seems very like, well, why do I need to know this? It is a bit like, well, how does this even come to play? Well, the reason so much that we know, like different gases, who does chemistry? A few people do chemistry? Yeah. So different gases have different, when we ionize different gases, they emit different lights, right? And when we look at different lights, right, and we use this experiment, we can calculate the wavelength of that light and we can actually identify different gases, which is really cool when we think about stars. Stars in the universe. How do we know that that's a star full of helium? Like, how do we know that? Because it emits a certain spectrum of light. And we identify that through looking at how, like what is the color that it is emitting, and then we can backtrack to figuring out, well, what is its wavelength. So this is big picture stuff. Okay? So for you guys, for now though, you're like, what do I need to know for the exam? Well, okay, you need to know how to utilize it. So given an example question like this, red light produced by hydrogen, right, and we've got the spectral strips, I'll get them out on Friday and we can have a bit of a look at them. Okay, it's produced by hydrogen, is passed through two slits that are 1.00 times 10 to the negative 4 meters apart. Right, so very tiny distance apart. You've got a wavelength, which is the red light from hydrogen, on a screen 3 meters away. So it's giving you, from here from the slits to the screen, 3 meters away. The distance between fringes is 1.97 centimeters. So between here and here is 1.97 centimeters. Find the wavelength of the light. Okay? So you take out your variables. I've got my equations. Again, you're going to have them on your formula sheet. So here, I know I need to find the angle first, because when I looked at here, I want to find the wavelength. Well, I know M is 1. It's kind of implied in the question that it's the first fringe there. So M is 1. I have the y distance between 1.97 centimeters. I know D, all right, I know D, but I don't know the angle, because it doesn't tell me. So I have to use my tan theta equals y over x to find the angle, to substitute to find that. So, oh yeah, no, that's here. So I substitute it in to find my angle. Once I found my angle, I can substitute into this formula to find the wavelength. Now, wavelengths are generally given in nanometers. Nano is times 10 to the negative 9. Okay? But both would be accepted unless it asked for the answer in nanometers. Okay, but 6.56 times 10 to the negative 7 is the same as 656 times 10 to the negative 9. And instead of times 10 to the negative 9, I can use nano. So both of these, 6 times 10 to the negative 7 meters, is the same as 656 times 10 to the negative 9, which we normally wouldn't use scientific notation like this. The only reason that we look at it like this is because we so often give wavelengths of light in nanometers. And the nano is the times 10 to the negative 9. Okay?
Oh, so you just give it in that.
Yeah, because here, I've shifted this decimal place 2 times this direction.
I got that.
Yeah, so 10 to 9. So then that is the same.
But it violates the rule of
It's
doesn't violate law.
It's just because light, visible light, is given in nanometers. That's just, yeah. So, we have D sine theta equals M. So my thing that I would do as you go through here is think this. So wavelength equals, I convert it straight to meters, 4.36. No, yes, that's
Do we have
400.
to use this one?
Sorry?
Do we have to use this one or it's fine without? Like you have to say 4 point.
Oh no, see, no, I was wrong. I started to do it the other way, but I'm like, no, straight away, just leave it like that and put it straight to times 10 to the negative 9. So make that as like a convert nano. So it's just normal meters by changing that. And then keep looking. First order means that M is equal to 1 because it's the first one. And I have a theta equal to 3.5 degrees. So I take out my information. Okay? I see Young's double slit experiment, so I know I'm going to be using this formula. I didn't go over dark fringes. Are you okay, Ronaldo? So what is the slit separation? The slit separation is the symbol D, is the distance between them. So it's looking for D. So here's my formula. Here are my variables. This is what I'm looking for, so I substitute. D equals, won't do it like that. D multiplied by sine 3.5 equals 1 times 436 times 10 to the negative 9. Okay, I plug this in. So D equals, plug it into my formula, into my calculator, 436 times 10 to the negative 9 divided by whatever sine 3.5 is, which equals, I've got the answer, yeah, 7.14.
What's going on?
This is like we started talking about quantum mechanics and like the idea everybody has a way of like it's. Woo. Okay, at what angle does the second order maximum occur? So the second part of the question is asking what angle does it.
You want me to withstand?
Yeah, so it's asking for when m equals 2.
Yeah.
And what is the theta when m equals 2? So I'm just going to substitute in. Same thing. So I've now got 7.14 times 10 to the negative 6 because I have d.
Can we use tan though?
Sorry?
Can we use the formula with tan? The other formula with tan?
No. No. Because you don't know the y, so you'll end up having to do this. Yep. So sine theta, this is the most efficient way. Okay? Because you need to have where you put 2 times 436 times 10 to the negative 9. So here now, I'm using the same formula, but now when it's asking for the second order maximum, that's asking for when m is equal to 2. And it's kind of inferred here that we are talking about the bright fringes. It will say dark fringes if it's talking about the dark fringes. So it's like, when in doubt, if it doesn't say something, it's talking about the bright fringes, and then the angle equals 7.01. Okay. So just one, no, just,
Oh.
sorry, here. I didn't really talk that much. Dark fringes occur half a wavelength compared to bright fringes. And that makes sense because it has to be here. It has to be at the point in which it deconstructs.
D is the piece of it.
Okay, so
D is just
that's the bright fringes has to be at the point in which they are 180 degrees out of sync.
Oh.
So that's where that's adding that half gets it 180 degrees, so they are deconstructing. Okay, so just keeping moving, the last thing so we can keep on time is the thing when it comes to double slit experiment is that you end up with quite large points in which you've had constructive interference. It may not be as bright as the central maximum or the ones out, but you end up with these large fringes because you've still got constructive interference. And there's really, with double slit, only one point in which you have absolute no light. But you end up with these quite large areas and spaces where you have constructive interference to a point. So they discovered that if we use diffraction grating, so hundreds, thousands of gaps, the way that the waves undergo constructive and deconstructive interference allows for much clearer points. So a diffraction grating is what we use to get much more intense, sharp points on the screens. So it really allows for that, intensity is maximum and very sharp and narrow. So it's that high resolution point of light because of the way that it undergoes the deconstructive. It really deconstructs more of it, so this is a lot less. And then you get a lot more constructive interference at a specific point. Now, diffraction gratings, the mathematics isn't any difference in any way apart from the D is the distance between two points, like two lines, and that D has to be calculated in a specific way. So here, if I look at this example, red light produced by hydrogen with a wavelength 656 nanometers is passed through a diffraction grating with 600 lines per millimeter. So what that's saying is that there is, what it's saying is that there is, can you guess it, 600 spaces for every 1 millimeter. So if you were to zoom in, there would be 600 like gaps in which the light could go through. So 600, that's really terrible. Let me start again. I'm trying to sort of make it so you can see. So there'd be like, here's the wavefront, 600 points in which it's undergoing diffraction. Okay? When we talk about the D, the distance, it's talking about the distance between the gaps. So this is the distance between the gaps. So for this question, red light, and we've got a wavelength, is passed through a diffraction grating with 600 lines per millimeter. So that means for 1 millimeter, there is 600 lines. So if I wanted to know the value of the D, the distance, okay, the little distance between one, it's going to be tiny, 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 but I would have to think about that. It is one line out of 600, and then I always have to convert millimeters into meters. So I convert this by going, I want 1 out of however many it is, and then I convert millimeters. It can sometimes be centimeters. So this does not have to have diffraction gratings in just millimeters. It can be any units. It can be centimeters. Generally, it wouldn't be meters because it'd be so many lines. It'd be like ridiculous. But I've seen lots of questions with like 10,000 per centimeter. Okay, different ones. Okay. Let's keep going. On a screen 3 meters away, find the distance from the central maximum to the first order bright fringe. So here, the light is shone through. The diffraction grating's here. And then you see it starts to spin out. This is the central maximum. Here, these are the first order fringes because they're the one out from the central maximum. So I take my data that I know. I know that it's a first order bright fringe. So that's 1. I know the wavelength is equal 6.56 times 10 to the negative 9, or 656 times 10 to the negative times negative 7 times 10 to the negative 9. Okay, distance 1 divided by the diffraction grating. Convert the millimeters into meters. Okay, the screen is 3 meters away. I'm trying to find the distance now from here to here. So I'm going to have to use my tan. Okay, I'm going to have to use the tan ratio. So I take my values, I plug in, I find my angle, and I find from there my y value using my trigonometry. Are you guys ready for one last bit of you guys doing some questions? 1 is false. Diffraction gratings are used to obtain precise measurements of wavelength of light.
True, false.
True. Okay? Because this stuff is known, so we know that wavelength of this value diffracts in this way. Like, we already know that now, hence why it's so useful with like chemicals. You ionize the chemicals and they'll emit a light of a certain amount because they're emitting photons. That's well, we're going there. It's going to be really exciting. Okay? Diffraction grating values are given in lines per millimeter. It's true, but is it always true? No. No.
It's still true.
It is, yeah, I know. Oh, it's a bit ambiguous. Okay?
True.
Yeah, it's kind of through.
It's not.
1,000 lines per millimeter. If it's 1,000 lines per millimeter, what is D for question 4? How am I going to do that? It's 1,000 lines per millimeter. Straight away, D is 1 divided by 1,000. But that's in millimeters. Right? Do I want it in millimeters?
2 times 10 to the power negative.
So I'm going to change this to 1 divided by 1,000 times 10 to the negative 3 meters. Now, I already know with the previous class, we started getting issues with our calculators when we got into too many, times 10 to the... Oh, this is Chris. Sorry, can we just go over this one? It's exactly the same.
So just take off that.
Yeah, take off that one. Yep.
Who's Chris?
Okay. Yeah, I know.
Oh my God.
Takes my question in terms. I wanted to do it in centimeters. And I'd already done this prep. I'd already done my prep sheet. Yeah. Okay, but good pickup. Yeah. Yeah.
Is this 25?
Yes, because it's not times 10 to the negative 3 on the bottom. Okay. So, my advice to you is when you look at this is you want to convert this into something much easier. So 1 divided by 1,000 is the same as 1 times 10 to the negative 3. And we times that by 10 to the negative 3. So we know that 10 to the negative 3 multiplied by 10 to the negative 3 is the same as what? 10 to the negative? Yeah. Alright. So I started looking at it, like some people got it, but sometimes you might have issues with your calculator if you're trying to do too much typing. So it's better to think, I want to get my D straight into something that's one number. Okay? At what angle does the first, so I'm looking for what angle does the first order maximum, so I'm looking for M equals 1, for a wavelength of 589.0 times nanometers times 10 to the negative 9 meters. So if I have these values and I know that D sine theta equals M wavelength, I'm just going to substitute in. So I take this and I substitute in. So I end up with 1 times 10 to the negative 6 sine theta equals, well this is just 1, 589.0 times 10 to the negative 9. So sine theta equals 589 times 10 to the negative 9 divided by 1 times 10 to the negative 6. So that ends up being 0.589, use the calculator. So theta ends up being 36 degrees. Okay? So have a bit of a practice with that. And just because I want to get onto our report and we're running a bit out of time, if you did the exact same thing, but instead of trying to look at can the second order maximum be calculated, the exact same thing, but you looked at now M equal to 2. So what happens when M equals 2? And you end up with sine theta equals 2 times the wavelength divided by 1 times 10 to the negative 6. You actually end up with an error. It doesn't exist. And think about that. Think about if I go back to the previous slide. There's going to be a point where it's diffracted so much, it's at that surface boundary, and it can't hit the screen. It doesn't exist. Okay? So just like we have the other ideas of critical angle with our refraction, there is a point in which you will not end up with fringes will stop because they'll be diffracting too far. Alright, because once it diffracts and bends, the next light could be that it's diffracted and it's on the boundary surface.
So there is no second.
There is no second. So if you type this into your calculator, you will end up with an error. It doesn't exist. Okay? So next thing is just making sure we have, sometimes the bright fringes can be referred to as N and not M. And sometimes the negative one will be referring to
The bottom.
exactly right, the bottom. So here you've got your slits in there and you end up with your lines. There's always your central maximum. But sometimes they'll refer to the point as being positive up or negative at the bottom. Okay? So that's,
Include the negative in the formula or
no, then you don't. That's generally where, or some textbooks don't, they just call them both m equals 1. Some just use it as negative, it's just knowing the position of it.
That's nice.
Yes?
So that is our final answer.
Yeah, it doesn't exist. So no, so the final example would be there is no second order maximum.
Oh.
Yeah. So that's that. Okay, so now, in terms of